So, good afternoon, ladies and gentlemen. Let's see, now it's working. A few months ago, the general manager of a company, of a water bottling company, called me. Says, Alberto, I've got a problem. I need you to help. So I say, okay, tell me what is happening. We met, and he told me a usual case. They were delivering pallets of water, and they were having problems in the last phase of the distribution cycle, in the last mile. They were loading the truck, and when they started to release some pallets, the remaining pallets within the truck were getting deformed, and they were getting even sometimes collapsed, okay? So we did a project with them, and the first part of the project was a research task. So I'm going to use this research task to explain you using this presentation, okay? The idea was trying to reproduce at the lab what was happening within the truck, okay? So let me start with a question that we ask ourselves in that moment. Now, is there a need? Sorry, it's working this. Sorry, it's not. Can you pass me the slide, please? Because is there a need to stress a unit load with vibration simulation in order to get a stability result closer to the reality? And if the answer to this question is yes, what we do? We do vertical vibration or multi-axis vibration? That was the question we wanted to answer also at the same time. So for doing this, I don't know what is not working this. So you pass me, okay? You help me. Okay, come on to the next one. So what we did was defining a process. We would first the transport monitoring of what was happening. Then we did the analysis of the transport, taking the data. Then we defined the test. Then we did the test. And then got the results, analyzed them, and got the conclusions. Okay? So, as you can see, come on, next one. We use one of the customer truck, a small truck, 9.5 tons, okay? And we took the worst case, was the last pallet in the truck, okay? And even we took the worst case in the route. We took the most hazardous route, okay? So indoor we place camera, high-speed camera videos, and also in records, our data loggers, to take all the information about vibrations, shocks, humidity, temperature, pressure, all the data, the GPS. So, come on, please. Yes, we set up the data recorders, our in-records. As you can see, we used two models. The one with GPS was installed in the truck, the big one, and the small one was installed within the pallet. And what we're looking for was the setup following the ISTA data analysis guidelines, okay, to measure the vibrations and the accelerations, okay, and also the rotational movements, okay? So then we launch and we follow the truck traveling. This is the starting part. This is the highway, but then we go into the local roads with curves and roundabouts, okay? It was about 45 minutes road, okay, because it was a last part of the distribution cycle, okay? And I will ask you to pay attention. We took now two moments. First one is the moment when we got the maximum deformation. Okay, you will see now the truck is entering a curve, and this is the moment where the pallet was getting the maximum deformation. Okay, and we will see later how we can measure this. Okay, and the other critical moment is, of course, please, the next one, which was the moment when the pallet was collapsing. Okay, so we measure also this moment. In that roundabout, you see the driver is doing a standard driving, nothing special, but the pallet was collapsed. Okay, so taking all this data that we recorded during the transport, we made analysis. And the analysis, how we did it. According to the ISTA guidelines, okay, we use the tool that is installed within the data lockers, within records. It's called Analyze, and we put the criterion to select the events. Okay, so in the vibration part, we chosen 10 seconds events. Okay, in the vertical vibration, we chose more than 0.01 GRMS. Okay, and for the pitch and roll, for the angular movements, minimum 0.5 degrees second RMS. Okay, this for selecting all this information for the vertical vibration axis and for the pitch and the roll. And in the part of the acceleration, we selected all the events higher than 300 milliseconds and higher than 0.2 Gs. Okay, so with this information introduced in the software, okay, we can analyze. Please go. No, it is a bit before. Sorry, before. It's a video. Sorry, it should be playing a video that shows you how it works. I don't know what is not working. Oof. Okay, then I will explain you, because it should be a video, okay, playing you that is showing you. Okay, so what you can see in the video is that, now it's working? Now, okay. So you have all the events that has been recorded, okay, and with all these events, okay, taking the limitations and the criterion we chose before, okay, is selecting all the PSD, summarizing all this information, okay? So it's a very intuitive tool that you can use very easily to select the PSD that is getting now, okay, the orange color. You have the PSD, and you can use any classical mode to analyze the PSD, the probability the spectra, or the distribution function, okay, or even we took the 100% of the testing of the recorder, because it was only 45 minutes, okay? So we took the 100%, okay, of the information, and with this PSD, for the vibration and the pitch and the roll, go to the next one, please. It is too much resolution for the machines, for the vibration machines, then we have to simplify it. So then we took all the interesting points of the recorded PSD, okay, to generate that more simple PSD for being able to reproduce into the machine, okay? So even you can introduce the limitations of your machines, their constraints, the maximum vibration, maximum stroke, and the system is preparing the PSD to adapt to the limitations of your machine it is needed, okay? So go to the next one. Finally, we got the PSD to be performed within the machine, okay? This table is representing the vertical information and the pitch and the roll information that will be introduced into the machine to make the test and reproduce what was happening during the trip, okay? Let's go on to the next one. Now pay attention to the acceleration. Using the same tool, the Analyze software, we could take all the information. You have the 3 axes, the forward direction, which is the channel 1. You have the lateral direction accelerations, which is the channel 2. And the channel 3 is the vertical axis. As you can see, in the vertical axis, we have no many events in acceleration, but in the forward, we have 7 events, but the most important events were caused in the lateral direction, okay, during the curves and during the roundabouts. If you pay attention to the yellow spot, that one was the maximum when I show you the maximum deformation of the pallet. That was the moment 0.37 Gs, okay? And the orange spot is showing you the collapsing moment. Even was a little bit lower acceleration, 0.36, and was happening 20 minutes later. So you can see that even was later, but was with low acceleration, 0.36 Gs, and the pallet was collapsing in that exactly moment. So I can show you the measures now, please, the next one. Here you can see the collapsing moment, and it's giving you the value of 0.36, okay, in the right moment what's happening with the collapsing moment. And the other one is showing you, using the InVision system, okay, we can measure the deformation. And in that moment was 372 millimeters. That was the maximum deformation that suffered the load during the transport, okay? So after we collect all this information and analyze it, we can make the test design, okay? The test design, we made 2 phases. First, the preconditioning, okay? So we took 20 pallets from the customer, 20 pallets, and we made preconditioning 5 pallets, 5 pallets, and 5 pallets. 5 of them non-preconditioning. 5 of them we apply the ASTM 4169, track level 2. The other 5 we apply ISTA, the pickup and delivery. And the other 5 we applied the PSD recorded and generated, as I explained you before, okay? So then we make the comparison, okay? After we make this preconditioning, about 40 minutes, we made this, we made the stability testing, okay? So for stability testing, we use the UMOS standard, which is the European standard for measuring and testing acceleration, and we increase 0.1 Gs by 0.1 Gs until the fatal fail. And on each test, we were measuring the static and the dynamic deformation, permanent and elastic deformation, okay? So I will show you now how we did it. We took each one, only one example to make it not longer, okay? But the results between the 5 were exactly the same, okay? So now, first we will see the preconditioning. In one image, I show you the vertical vibration. This is the machine, this is the machine we use that can be used for vertical vibration, only pitch and roll, or vertical plus pitch and roll. So we will use that way, vertical vibration, and this way, vertical plus pitch and roll, okay? This is the machine we use for doing the preconditioning in the vibration time. Then we will use these graphs. Okay, you will see the preconditioning with ASTM and ISTA pickup and delivery, which is about 5 times more GRMS than the one we recorded and the real one, as you can see. But pay attention that the blue one, the real processed data, is going to be simultaneously combined with the pitch and the roll, which was recorded. So we will compare this with the ISTA and ASTM 4169, okay? So now we go to the acceleration. We will use this compact unit for doing the acceleration test, okay? And we will use a system, go to the next, please. We will use a system for measuring the deformation, the static and elastic. Let me tell you that the static deformation is just after the test, how it's keeping the load. And the dynamic or the elastic deformation is the worst moment during the testing. As you can see, there is an orange frame. This is the limits established by the UMOS standard, which is 10% of the height of the pallet during the elastic, during the movement, and 5% after the testing, okay? This is the maximum deformation allowed to consider a stable pallet or a unit load, okay? And finally, we got the report, which is giving you the information. This is an example, okay? That is telling you that permanent deformation, maximum limit is 71 millimeters, and you got 17 on this example. Is a load stable, it's okay. And for the elastic deformation, you got 211 millimeters, and the limit was 143, okay, which is not okay. This is an example to show you how it works and how we generate the reports to do this testing, analyzing. So let's go to see the preconditioning. We do the testing, okay. Yes, please. Now you see we are doing the preconditioning test. The ASTM, please switch on the video. No, the one before. Play. It's not working. Well, on that side, it's playing with the ASTM, vertical vibration. On the center is the ISTA, vertical vibration, pickup and delivery. And in the right side, it's the pitch and roll plus vibration. Now. Not this one, the next. This one, yes, please. It's not working? Okay. It's not working. So let's go to the next, if I cannot show it. Okay, after the preconditioning, the vibration, preconditioning and vibration plus pitch and roll, we did the acceleration test, okay? That was the 0.1 Gs, okay? As you can see, it's very soft, okay, but we started with this for all. You will see non-conditional sample in the right, in the left upper corner, the vertical plus pitch and roll recorded PSD here, and here are the ISTA and the ASTM, okay? So as you can see, more or less, and this is 0.2 Gs acceleration, okay? So it's moving a little bit more. The one was preconditioned with the vertical plus pitch and roll than the other three, okay? We go to the next one, please. Here you can see the 0.3. They are moving a little bit more, all of them, but some, for example, the vertical plus pitch and roll is reaching the limit, but as I told you before, we are not looking now for a stable load. Where we are looking is for the fatal fail, for the failure mode. So we are looking this, but all of them are close to the limits according to the UMOS, and we will see now the 0.4 Gs, okay? Here you will see that the three of them are still keeping alive. All of them, please. This one also. No, my God. No. Okay, play. Are working all of them. Okay, thank you. And you will see that the vertical plus pitch and roll at 0.4 Gs is losing and collapsing, okay? The failure mode is the same that we saw within the track, okay? The other three are keeping still alive, okay? So let's see now, we keep going on, okay? The next one, then we see we got the fatal fail at 0.4 Gs. They are quite deformed, but not failure mode are reached again, still, sorry. We go to the 0.5 Gs, looking for the failure mode of the rest of the pallets, okay? So we can check that all of them are going to reach the failure mode in the same way also, okay? So finally, we go to the next one. We got at 0.5 Gs, these three preconditioning loads, the fatal fail, and the one before, the vertical price pitch and roll at 0.4 Gs. Okay, let's put this on the graphs. Let's go to the next one. We analyze now the results that after testing, okay? Yes, as you can see, this is the permanent deformation, that side, which means after the testing. Even at 0.2 Gs, all of them were in the same behavior, but at 0.3 Gs, the preconditioning with vibration plus pitch and roll was getting more deformed. If we go to the elastic deformation during the test, we see that from 0.1, the preconditioning with vibration plus pitch and roll was higher deformation than the other three, which were having more or less the same behavior up to the moment, after this moment is collapsing, okay? And the other three were keeping in the same behavior. So, go to the next, please. So, if we put in this graph, the maximum recorded deflection, remember that was 372 millimeters, that was the maximum deflection, and the moment when the pallet was falling, this moment was at 0.36 Gs, okay? If we put our preconditioning loads and testing loads, we get that, sorry, oh, okay. So as you can see, if we extrapolate, we are getting that at the maximum deformation supported by the load, which is the moment is collapsing, the preconditioning with vibration plus pitch and roll is at 0.38 Gs. The other three preconditioning with vertical vibration, ISTA, ASTM, and non-preconditioning were failing at 0.42 Gs. Remember that we made the test 0.4 Gs and 0.5 Gs, but we jump from 0.1 to 0.1. Now it's telling here in the graph exactly in what moment was happening its collapsing moment, okay? So go please. There is the conclusions we got, okay, from the analyzing is that this study is giving us the confirmation that the HUMOS standard is working to make all these tests, acceleration tests, to get a closer testing to the reality. Okay, the next conclusion is that there is a correlation, a concordance between what is happening within the lab comparing what is happening during the real transport. Okay? The other conclusion is that, as you can see before, we got maximum acceleration of 0.37, okay? In that moment was not failing the load because there is a failure which is made by the cumulative stress from the vibrations and the accelerations. So finally we got the collapsing at 0.36 Gs, which was not the maximum acceleration during the distribution cycle, was later, okay? And finally, the preconditioning using the vibration plus pitch and roll was the one who got much closer to what was happening during the real transport, the collapsing, because we got up 0.38 Gs, the collapsing of the load, which is closer to 0.36, which was the real figure, more than 0.42, okay? So what is telling this to us is that, go on, coming back to the question I was asking, I'm wondering at the beginning of the presentation, is there a need to make a vibration to get a real a load, in order to get a stability result closer to the reality? We could say yes, and of course, if this question is yes, what we should do? In this case, we can see that doing multi-axis testing is getting us closer result than using only vertical vibration. So that makes us to think in ISTA, go on please, that enhances the need to move forward in the study for the new protocol for multi-axis. ISTA is in this moment doing this, is working on this protocol, and also HUMOS is also working on the multi-axis protocol, okay? With regard to our customer, I could say you that after this testing, we redefine the stretch film they were using, we changed to another one more expensive with higher quality. And in opposite, that was getting savings of about 120,000 euros per year because they were moving 1 million pallets. In despite of using a more expensive stretch film, but using quite much less quantity of stretch film, because using this testing, they detected with a better quality and less amount, they can get a more safer unit load. And additionally, they reduce the wrapping protocol, the number of turns, which got reducing time of 1,500 hours per year in the using of the wrapping machine. That makes reducing of energy consumption. So we measured the reduction of emissions of CO2. It was 185 tons per year, thanks to this study. Thank you very much, and excuse me for the technical issues, okay? I try to do my best.